Okay, so the example we finished up with last time was an example of a function sequence that converged pointwise to a function f, where every member of the sequence was continuous, but the function they converged to was not continuous. And so we mentioned that, sort of mathematically speaking, that's not something we want to see. We would like continuous functions to converge to continuous functions. And so we have now a stronger notion of convergence called uniform convergence. So let's take a look at what that definition says. All right, so first off, we're going to denote uniform convergence with a double right arrow. I don't know that that's standard notation, but I like it because it emphasizes that Fn is converging to F, but it's doing it in a stronger way, right? We have double arrows. So we say Fn converges uniformly to F on A if for every epsilon bigger than 0, there's some capital N, such that if we go far enough out in the sequence, so if n is bigger than or equal to capital N, then we've made Fn within epsilon of F, and here's the crucial part, for all x in the set. Right? So this happens for all x in the set at once, and so crucially, we have 1n sub epsilon for all x at once. In other words, we can make f of n uniformly close to f on the entire set if we go far enough out in the function sequence. Right? So that's going to be our notion of uniform convergence, and now it's our job to show that this was worth it. So if f sub n is a sequence that converges uniformly to f, and all the fn's are continuous at c, then the resulting function f is also continuous at c. Right? So this distinguishes uniform convergence from the pointwise convergence we saw earlier. All right, so let's prove this. Okay. Let epsilon be bigger than 0. Then, by definition, there exists capital N such that if I go that far out in my sequence, I can make the function difference less than epsilon over 3. And this is true for all x in A at the same time. All right. Also, by definition, since this function f sub capital N is continuous at c, there exists some delta such that x minus c less than delta implies f capital N of c, f capital N of x minus f capital N of c is also less than epsilon over 3. And now we finish up by showing why epsilon over 3. So note that if I look at f of x minus f of c, right, I'm trying to show I can make that less than epsilon, thereby showing f is continuous at c. All right, so if f of x minus, so considering f of x minus f of c, I can rewrite this as f of x minus fn of x plus fn of x minus fn of c plus fn of c minus f of c. So I've, inside the absolute value, I've added the clever form of 0, right? I've added and taken away fn of x, and then added and taken away fn of c. And now I split that up with the triangle inequality into three pieces, each of which I will show is less than epsilon over 3. Okay, so with n as before and delta as before, if x minus c is less than delta, then what I get, with the capital N I selected before, by uniform convergence, this first piece is less than epsilon over 3. By the continuity of f sub capital N with the delta chosen as before, the middle piece is less than epsilon over 3. And then by the uniform convergence again, the last piece, right, is using a value for c that's also in the set A. And remember, the uniform convergence works for all x and a at the same time. So fn of c minus f of c is also less than epsilon over 3. And that equals epsilon as required. So if we have a uniformly convergent sequence of continuous functions, the limit function has to also be continuous. Now, this is actually a really useful theorem if you are attempting to show that convergence is not uniform. If you think about our previous example, the only example we did last time, we had a sequence of continuous functions that converged pointwise. And we might be interested in knowing whether or not that convergence is uniform. Now, we showed that the resulting function, the limit function f, was not continuous. So by this theorem, the convergence could not have been uniform, right? If the convergence was uniform and f sub n was continuous, then so has to be the limit function f. So if the limit function f is not continuous, the convergence can't be uniform. All right, so next up we'll do an example of showing uniform convergence from the definition, and then we'll talk about what's called the Cauchy criterion for uniform convergence.